Welcome to section 1.4 on quadric surfaces. The goal of this section is to become familiar with the graphs of the principal quadric surfaces and eventually to be able to sketch the graph of a given quadric surface with its equation as given. So we're going to do in this video section 1.4.1 the definition of a quadric surface and 1.4.2 taking a look at what the graphs of quadric surfaces look like. So let's start with the definition. A quadric surface is the graph of an equation of the form ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j equals 0. That's the general second degree polynomial in three variables. So a little note though, we're not actually going to study equations quite so complicated. Equations with mixed terms x, y, yz, and xz are graphs that are rotated with respect to the coordinate axes. We're not going to study equations of these, so we can sort of get rid of mixed terms like that. And in general, we are going to focus on equations with at most 4 terms, either 3 second degree terms and a constant, something like ax squared plus by squared plus c z squared is equal to d, or even 2 second degree terms, 1 first degree term, and a constant. So something like ax squared plus by squared plus c z to the first power is equal to d. And equations of these forms are more often than not going to be centered at the origin. So just a little remark here, quadric surfaces are actually the two-dimensional analogs of graphs that you probably studied in high school, and those things are the conic sections, things like circles and ellipses and parabolas and hyperbolas. And we're going to review these curves soon. But what we're going to start with is taking a look at the graphs of some actual quadric surfaces. So in example 1.4.1, we are asked to draw the shapes of the following quadric surfaces without a coordinate system, just a drawing, and to identify the traces of conic sections, so things like circles and ellipses and parabolas and hyperbolas that can be found on each surface. So what we're going to do first of all is look at an actual graph of one of these objects, and then we're going to go and just practice sketching the shape. So let's go first and look at the graph of a sphere. Notice that all of the curves drawn on the surface of the sphere are circles. And now let's practice drawing the sphere. So a sphere is a ball. You might draw it sort of looking like this. And if we're asked to look at traces of conic sections, well, any cross section or any cut that you take of the sphere will always give you a circle. So the only conic circle with section with traces on the sphere is a circle. Let's go now and take a look at the graph of an ellipsoid. Here's the graph of an ellipsoid. Notice that all of the curves drawn on the surface of the ellipsoid are either ellipses or circles. And now let's practice drawing an ellipsoid. So it's not perfectly round. In fact, it is an ellipse, hence the name, but it's an ellipse in 3 dimensions. It's a little bit like a football shape, or like a capsule, a pill that you might take for a headache or something like that is an ellipsoidal shape. And so if you're looking at the traces of these things, cross sections, well, you do definitely have ellipses. But depending where you look in those cross sections, you may also get circles. So let's go now and look at the graph of an elliptical paraboloid. Here's the graph of an elliptical paraboloid. Notice that all of the curves drawn on the surface of the elliptical paraboloid are parabolas and ellipses. And now let's practice drawing an elliptical paraboloid. So these things make me think of like a goblet top, a wine glass or something like that. So obviously this one goes on forever, right? I've just drawn it as if it's cut off here, but this graph doesn't stop. It keeps on going in all those directions. It does stop here at the bottom. If we were to look at cross sections of this, well, as it's in the name, you certainly do have ellipses. You also have, and you might have guessed it again by the name, parabolas. Next, let's have a look at the graph of a hyperboloid of one sheet. Here's the graph of a hyperboloid of one sheet. Notice that all of the curves drawn on the surface of the hyperboloid are hyperbolas and ellipses. And now to draw the hyperboloid of one sheet, you imagine sort of this thing looking like a nuclear cooling tower. That's the stereotypical shape that these things have. And the traces, the conic sections that are involved are ellipses. Ellipses, or they could be circles, depending if they're perfectly round or not, and hyperbolas. So if you don't remember the conic sections and what they look like, we're going to review those in just a bit. But hyperbolas is what I've drawn in green here. Again, these I've drawn them as if they end, but this is part of an infinite shape. Right? This goes on forever here as a big hollow tube. Now, hyperboloids come in different versions. So this is a hyperboloid of one sheet. Let's go and take a look at the graph of a hyperboloid of two sheets. Notice that all of the curves drawn on the surface of the hyperboloid are ellipses and hyperbolas. And now to draw the hyperboloid of two sheets, we're imagining that this cooling tower went on a bit of a diet and its center got skinny and actually got so skinny that it split apart and became two separate pieces. And that's what you have here, the hyperboloid of two sheets. So you might not be surprised to see that you still have ellipses or circles, and you still have hyperbolas. Although the shape of the object is a little bit different, so we still have hyperbolas, and we still have ellipses or circles. And the same thing, right? This is not a closed object. This is an object that I've just drawn a portion of that continues. The double cone. Well, the double cone you can think of as the hyperboloid of one sheet just before it splits into a hyperboloid of two sheets. So let's go and take a look at the graph of a double cone. Notice how the sides are straight and they look like two straight lines. And all of the curves drawn on the surface of the cone are either ellipses or hyperbolas. And now to draw the double cone, well, you start out the exact same way, except you don't have curvy sides. Here you've got straight sides. And in the double cone, you have the ellipses. If you were to take a cross section that sort of shaved down the side, you would still have hyperbolas. And you would also have, right on the edge, you would have two parallel lines, which actually is kind of a degenerate hyperbola. So we do have hyperbolas, including two straight lines. And we do have our ellipses and circles. Not and, or circles. And the last one is the strangest one of the bunch in a certain respect. It's the hardest one to draw. So let's go have a look at the graph of a hyperbolic paraboloid. Looking a little bit like the saddle you might find on the back of a horse. Notice how the curves drawn on the hyperbolic paraboloid are all either hyperbolas or parabolas. Okay, to draw a hyperbolic paraboloid, it's hard to explain exactly what to do. You probably need to start the video and follow my pen strokes to get an idea of exactly how to draw this. You're imagining this looking like the saddle on the back of a horse or something that you might sit on to ride. And there is the basic shape of this. And as the name suggests, it is built out of hyperbolas and parabolas. So we have here hyperbolas and parabolas. So let's finish off this section by taking a quick stock of these traces that we've found on each of these objects. They're going to be useful for us when we want to graph these things given their equations later. So a sphere is built entirely out of circles, or has cross sections or traces which are circles. The ellipsoid is got traces, or has got traces that are ellipses and circles. A paraboloid, you will find ellipses or circles and parabolas. Hyperboloids and the double cone, you will find ellipses or circles and hyperbolas, including two straight lines in the case of a double cone, two degenerate, I have trouble with that word, degenerate hyperbolas. And the last thing, hyperbolic paraboloid, you'll find hyperbolas and parabolas. Okay, that's it for for the first two subsections of quadric surfaces. We're going to explore them a little bit more in the next couple of videos, including how to graph them properly when you're given only their equations.